In the previous sessions, we begin the theory of Gelfand or Gelfand theory, and we see the definition of characters. Let A be an algebra. A character on A is an epimorphism such as phi from A to complex numbers. Thus, a character phi is a non-zero linear functional on A such that we have this equality. So this phi is linear and also is multiplicative, because this must be epimorphism, okay? Phi is a non-zero linear functional such that this linear function characters are sometimes called multiplicative linear functional, and we write phi by the index A for the set of all characters on A, and phi A is called the character space of A, okay? If A has an identity, then it is clear that phi of EA equal to 1 for all elements in phi A. If phi be a multiplicative linear functional, then phi of EA must be equal to 1. And also we see this example, and we have this notation for any algebra A. If phi belong to phi A, if phi be a characters on A, we write M by the index phi equal to the kernel of phi, or the set of all A in A such that phi of A equal to . And also we have this proposition, let A be a unital algebra, then the map phi to M phi is a bijection from phi A onto the set of maximal ideal of codimension 1 in A. And we see this in the previous sessions. To M phi from phi A is from phi A to the set of all M such that M is a maximal ideal in A, or more precisely maximal ideal with codimensional or codimension 1 in A, and we denoted this set by capital M, okay? Capital M. So we can write phi A to is M equal to the set of all maximal ideal with codimension 1 in A. And after this proposition, to phi A, then phi is continuous and the norm of phi equal to 1. In this book, there are two proofs for this theorem. First proof, the maximal ideal in phi is closed by proposition 2 to 1, and so phi is continuous. For linear functions, we know that phi is continuous if and only if the kernel of phi be closed. The kernel of phi be closed. Okay? And we know that phi or the kernel of phi is closed, so that phi must be continuous. And for the second proof, for the proving that phi is continuous, we can prove that this phi is a bounded operator. Okay? Theorem. If phi belong to then phi is continuous and the norm of phi equal to 1. Okay, we have this theorem. For the proof, since phi is a linear map, we know that phi is continuous if and only if phi is bounded. If it is not bounded, we have there exists an element in A such that the norm of A is less than y, but this is equal to 1. There exists A in A with these properties. The norm of A is less than y, and absolute value of phi A equal to 1. This holds because if this statement not hold, let me denote this by a star, for example, is by a star, okay? If a star is not whole, then we have for any A in A, we have these two properties. For any A in A, such that A, the norm of A is less than 1, for example, norm of A is less than 1, we have norm of phi of A non-equal to 1. And this shows that the norm of phi must be bounded, okay? Yes, students, let me a minute. Okay, sorry dear students, and this implies that is not hold. We have this, and this implies that P is bounded, or we can write by a simpler method. Sorry, because since norm, okay, so that the norm of phi equal to the supremum of all absolute value phi of a, such that the norm of a is less than or equal 1, and we assume that phi is not bounded, so that this is equal to infinity. And it shows that for any n in n, so there exists an element in A with this properties that the norm of an is less than or equal 1, and this phi A equal to n. Now if we consider A equal to an divided by n, we see that if we consider this, then we see that the norm of A equal to 1 divided by n multiplied by n, and phi of A equal to let me write this in this line, and absolute value of phi A equal to absolute value of phi of an divided by n, and this is equal to this, because phi is a linear map. Okay, phi is a linear map, and this is equal to 1 divided by n, absolute value of phi an, and this is equal to 1 because this is equal to n. So that for an element such as A, such that the norm of A is less than y, and is equal to 1. And also we can assume that phi of A equal to 1. Phi of A, okay, because phi of A divided by phi of A equal to this, because phi is linear, so that this is equal to 1. Now by theorem 1, 4, 2, there exists B in A with this property, because we see that if the norm of A is less than 1, then EA minus S minus A must be invertible, okay, must be invertible, so that this element must have an inverse. So this multiplication equal to the identity map, and we have phi of B minus phi B minus phi A must be equal to this, and this is very trivial, because since the norm of A is less than 1, EA minus A is an invertible element of A, so that there exists an element such as B in A such that B multiplied by EA minus equal to the identity map, so that phi of this equal to phi of this. So E of B E A minus A must be equal to E phi of EA, and this is also phi, not P. Phi of this element equal to phi of this element, and so phi of B, phi of EA minus A must be equal to phi of EA. And phi of EA minus B equal to let me write phi of B minus phi of B multiplied by phi of EA equal to phi of EA. It is trivial because this equal to this equal minus BA, so that this is phi of B minus phi of BA, and phi of BA equal to phi of B multiplied by phi of A. Phi of A, okay. What? Phi of A equal, and this is equal to 1, and this is the introduction. This is a contradiction, because we reach to this rank inequality. This equal to 1, but this is equal to 0. This contradiction shows that this assumption is not whole. So phi is a bounded, so phi is a bounded linear map and so it is continuous. Okay, it is continuous. And also or equal 1, and since we know an element such that phi of A equal to 1, this must be exactly 1. Okay, this must be exactly 1. Okay, we thus see that phi A is a subset of this space, the set of all elements in the dual of A such as lambda of EA equal to 1 and the norm of phi equal to 1, or more perfect, we have this conclusion. For any phi in phi A phi of EA equal to 1 and this is equal to the norm of phi. Okay, and the set of all elements in the dual of A with this property is called the state S. And we see that in the Wikistar topology on the dual of A, we have very useful properties. Let me recall the Wikistar topology definition. Let A be a norm space and A prime be the dual of A. We know that A prime is a complete node space the operator node. If we consider, let me add a notation, if for each A in A we define A tilde from A prime to C by this function rules. For each phi in A prime, A hat of phi equal to phi of A. Okay, please note that phi of A is element dual of A. Okay, phi belong to A prime, so that phi is a function from A to C. Okay, and A is an element of A, so that phi of A is defined. Phi can be act on A, and this is a well-defined function. If for each we define, then this is an element in the second dual of A. This is equal to the dual of A prime, the second dual of A prime, the dual of A prime or the second dual of A. And this is very easy because it is very trivial that this is linear. For example, A hat of phi 1 plus phi 2 equal to phi 1 plus phi 2 of A, and this is equal to phi 1 of A plus phi 2 of A, and this is equal to A hat of phi 2. And also for any alpha in or scalar field, and for any phi in the dual of A, alpha phi equal to alpha phi of A, and this is equal to alpha of phi A, and this is equal to alpha of a hat of phi, so that this a hat is a linear map, and also this is so a hat is a linear map from A prime to C, and also A hat is bounded or continuous. Okay, prime if the norm of phi is less than or equal 1, then A hat of phi or phi of A is less than or equal the norm of phi multiplied by the norm of A, and this is less than 1, so that this is less than the norm of A. So the norm, the operator norm of A hat, okay, this is equal to the supremum of A hat of phi, such that phi belong to A prime and the norm of phi is less than or equal 1. But for any phi in A prime with this property, we see that this is less than the norm of A. So this is less than the norm of A. This shows that this is bounded. And so for any A in A hat must be belong to the dual of A prime. Okay? Therefore, we have these functions in the following, or books denote G, for example, or any other notation you can use. Function let me write this H, okay, from A to dual of A is denoted by A prime prime, okay. By this function rules, H of A equal to A hat, because we see that A hat is an element of the second dual of A. Now, the weakest topology on which is topology or the S ballast, okay? Topology on a param that all elements in this space, the set of all A hat such that A belongs to A, be continuous is called the weak star topology in the dual of A. Okay, please note that for any A in A, we have A hat is an element of the second dual of A, and so A hat is a linear bonded functional from A prime to C. Note the weakest topology on A prime such that these maps are continuous. All of these for any A in A must be continuous. Okay? And the weakest of topology on A denoted by sigma of A prime and A. The weakest of topology in A prime is denoted by sigma of A prime and A. So if phi n, for example, is a sequence in A prime, and also phi be an element of A prime, we have phi n converge to phi in the weakest star topology if and only if, or this is equivalent to, is fact that for any A of phi tend to A hat of phi n tend to A hat of phi, or equivalently for any A in A, phi n of A tend to phi of A. And this is very applicable properties for weak star topology. Okay, and also we have the Banach-Alaoglu theorem. Let me recall this for you. Theorem. Banach-Alaoglu theorem. The closed unit ball in A prime is compact in weak star topology. And you know that closed unit ball A prime 1 example, okay, by the notation in our book, this denoted by A prime 1, okay, in A prime is compact in the weakest star topology. This is a very famous theorem, and I recall again that A prime 1 equal to the set of all phi in the dual of A such that the norm of phi is less than or equal 1. Okay, we have the Banach-Alaoglu theorem. Now we can read this paragraph. The weakest star topology on A prime is denoted by sigma of A prime and phi. That we define this topology for you. So lambda v tend to lambda in this topology if and only if this tend to this. Recall that the unit ball of A prime written by this is weak star compact. This is Banach-Alaoglu theorem. The space phi A, the space phi A is taken to have the related weak star topology from A prime, and we shall call it is the Gelfand topology. The weak star topology in A prime is called the Gelfand topology, and this is the notation of A hat. Take for any A in A hat as a bounded linear functional on A prime by this functional rule. A hat of lambda equal to lambda of A for any lambda in the dual of A. The definition of the weak star topology shows immediately that A hat is continuous on this. This is exactly the definition of weak star topology. Okay. And let me state this theorem. The space of VA is compact in the weak star topology. Okay, because we know that phi A, okay, phi A, phi A is set of the dual of A prime. We have this theorem. VA is compact in the weak star topology of A prime in this space, and its proof is easy. For each A and B in A, define K by the index A and B equal to the set of all elements in the dual of A such that we have equality, and also define K of EA equal to the set of all lambda in A prime such that lambda of EA equal to 1. Then each KAB and KEA, all of these sets are compact. It is very easy because all of these sets are closed subsets of the unit ball of A prime. Okay, it is not that K of A and B is a closed subset of the unit ball A prime bond, and also KEA. Okay, and we know that this is a weak star compact. Okay, by Banach-Alaoglu theorem, this is weak-star compact. So that this closed subset of this compact set must be compact. K of EA and K of A and B are compacts. Compact sets. And clearly phi of A equal to the intersection of these sets. Any element of phi of A or any characters have these properties and vice versa, because any element of phi of A must be multiplicative and the lambda of EA must be equal to 1. And we know that all of this is compact, all of these are compact. We know that the intersection of compact sets are compacts, and the intersection of any family of compact sets is compact, so that this is a compact subset of A prime. Okay, we continue Gelfand theory. In the next session we expect some definition and notation, and we can continue in the next session inshallah. Dear students, okay, thank you very much.